Oh, brilliant. Look at the mess on my desk. I seriously need to think about tidying some stuff up. This is what happens when you experiment with electronics. You end up with a messy bench. Greetings, the Astro 30 here yet again with another, experimentation video. Messy desk aside, I've actually cleaned that up now, so there's less junk sitting on top of the desk. Today we're going to look at the series pass regulator using a transistor, as I did in a previous video, which I'll link up the top. And in this experiment, we're going to look at what's known as an error amplifier series pass regulator. That's where you use an error amplifier to maintain the voltage on this transistor as close to the desired output voltage as possible, so it's not varying up and down due to different load requirements. So I'll just go through a quick explanation here. We've got a voltage reference formed by a resistor and a Zener diode, and that can be anything in this case. At the moment I'm using a 5.1 Zener and about a 1K dropping resistor here. This provides a voltage reference to the non-inverting input pin of any standard op amp. I'm using an LM833, and that has a maximum supply voltage of plus minus 18 volts. The output directly drives the base of the output stage transistor, and the inverting pin comes back through this resistive divider which comes off the output and that between ground. And if these two values of a resistor are the same, then we now will get an output voltage that is double the reference voltage. So say the reference voltage is 5.1 volt, we should see 10.2 volt here on the output. Why? Because if you think about this, this error amplifier is configured as a basic non-inverting amplifier, where we've got a feedback resistor and a gain resistor. Now we can then apply the gain formula for a non-inverting amplifier, which is gain equals 1 plus R1 divided by R2. So if you divided, say these were two 100Ks, 100 by 100 is 1 plus 1 is 2. So this amplifier is operating at a gain of 2, hence why we have an output of 10.2 now. With the voltage reference, we can use anything else other than a Zener diode. We can use a dedicated voltage reference IC to provide, say, I don't know, 2 volts, 3 volts, whatever you want. So whatever reference voltage you have here is kind of irrelevant. We can also make this feedback network here variable. Therefore we can vary the output voltage from the reference voltage to, well, whatever's coming in. So this error amplifier will also take into account the 0.6 of a volt drop between the emitter and base junctions of this transistor and correct it. So let's have a look at a breadboarded experiment. And it's breadboarded here. I did all this yesterday. I've basically prepared ahead of time here. I'll just go through the various different parts we've got here on here. I've got a supply line bulk filtering capacitor here, a little LED with a 10K drop-in resistor going to the negative input, so I can actually see the circuits operating, because the supply leads that come off the supply are kind of junk. I've got a BD139 transistor here connected to a TIP35C as our output stage transistor, and that's connected as a Darlington configuration. It just boosts the gain of this output transistor. Down here I've got the LM833 IC with a supply line bypassing cap, a little 100 nanofarad capacitor across both supply pins, just to help keep the op amp stable. There's a 1 microfarad 100 volt capacitor, it's the only one I had to hand, on the output side of the regulator circuit, just to try and keep the output stable. I've got two 0.22 ohm resistors in parallel to form roughly 0.1. This is going to be used as a current sense resistor for basically trying to implement a short circuit protection for the output here, because otherwise if there's no output short circuit protection, during my tests I had about 6-7 amps going across the load, so that's not going to make the output stage very happy. And that's pretty much it really. There's not much else to explain. There's a few other extra components up here, we'll ignore them for now, that's not important. The emitter comes into one side of the resistor and the output's on the other side of the resistor, and our feedback network for the op amp comes off of this side of that resistor, so it also can correct for the drop that's going to be experienced by that particular resistor. Supply is hooked up and it's at its maximum 15.5.6. Turn it on. And this meter is not very accurate. It says it's drawing 100 mA and it's not really doing anything. I've got my multimeter set to the voltage DC scale on the fastest ranging speed. And as we can see, we've got an output of 10.486 volts. And it's varying up and down. But that's only because the op amp is actually correcting the output, so it is going to be constantly going up and down, which would also have something to do with the way this is laid out and all these wires going everywhere. Anyway, I've got a couple of resistors over here to test. I've got a 22 ohm resistor here and a 27 ohm resistor. So the output's at 10.492 now. I'll connect up the 22 ohm resistor. As we can see, it dropped down by about 12 millivolts, which is not bad. Now, if that error amplifier wasn't there, that would drop out a lot more. And currently, it's drawing about 600 mA. Not sure how accurate that is. It's probably more like 550. But if we did Ohm's law on that resistor, for the voltage that's going into it, we could calculate what the current is. So I need to calculate the current. So that's current equals voltage divided by resistance. So it's not that, it's 10.49 roughly, divided by 22 ohms. Yeah, that's a current draw of 476 milliamps, which is not exactly what it's saying on the supply. So if I now connect these two resistors together, it's a 27 ohm and a 22 now in parallel, connect up the load, drop down by about 20 millivolts, and the supply is saying it's closer to an amp. So I'll just disconnect that because that is going to dissipate quite a bit of heat. So now I need to calculate what the ohmage of that parallel resistance is and also what its current is. Yeah, so according to this, about 12.122 ohms. So I'll just say 12 ohms for the sake of argument. So 10.49 divided by 12 ohms gives us a current draw of 874 mA. So yeah, the amp meter was pretty close when it said 0.9. But the whole entire point to this circuit is that the error amplifier corrects for different load dependencies. That's the load connected, that's the load disconnected, connected, disconnected. I do have a 1 ohm resistor here, which is probably not going to make this circuit very happy, because at 10 volts across 1 ohm, that's 10 amps. And I don't know if that output transistor can handle it. But I've got plenty of those, so if I destroy it, well, I destroy it. As we can see now, the voltage dropped way off. That's only because it's drawing quite a fair bit of current. In this case, 5 amps. So that's pretty significant, and it's just going to show that the output transistor now is being saturated and it can no longer produce that amount of current. It should be producing 10 amps, but it can't. If we had a better output transistor that could dissipate a lot more current, these are supposed to be rated at 25 amps, but yeah, in the real world, yeah. And I know that supply that's powering the circuit is good up to 40 amps, probably more like 20 amps. So it should be able to handle it, but it can't. That is, the power supply can handle it, this can't. So that's our first limitation with this particular circuit. is when it starts drawing a lot of current, the voltage will drop off. Now remember I said we can make the output variable between the reference voltage and whatever's coming in. Well, I've removed the two 100k fixed resistors from the divider network. The center wiper of this 50k linear pot is going to pin 2. The clockwise position is going to ground or common, and the counterclockwise position is going to the output after the current sense resistor. The reason why it's wired in reverse configuration as you would think is because when you actually rotate the control down to counterclockwise, the voltage increases just due to the way the amplifier is correcting the signal. So currently the potentiometer is around about halfway. If I turn it up, we get to about 13.7, so we're losing a little bit, like 2 volts or so off of the supply, which is perfectly understandable. Now if we rotate it the opposite way, so we're turning it down now, there's our reference voltage of 5.2 volts. So I can move my multimeter probe to the reference voltage, and as we can confirm, the output voltage at that is 5.2 rather than 5.1, tolerance of components. So we can see that the output is exactly following what the reference voltage is. Change that back again to our output, bam. So all very good. We could also substitute this reference voltage for, say, another variable power supply and actually get a more stable reference voltage going in there, which may solve the problem of the output going up and down in voltage. So let me hook up another power supply in place of this Zener network. All I've got to do is just remove this wire going to pin 3 of the op amp and put a positive signal in and a ground, and yeah, that's basically all we need to do. So I've got my variable bench supply that I'm building set to roughly 4 volt going in place of the Zener diode. Currently with the pot almost central, I'll put that back to central. We've got more like 8 volts coming out, which is to be expected. Turn him up, got the full supply voltage out, and our reference voltage at minimum. And well, it's still moving up and down a bit. Again, that supply is not exactly accurate either. But why is the pot doing what it's doing? Well, basically it's controlling the feedback to the op amp from the output. So basically when this pot is at 0, we've got 0 ohms across these two connections. That is essentially putting our feedback resistor as 0 ohms within, 1 or 2, maybe 10 ohms. That now means that this op amp, for all intents and purposes, is now operating as a voltage follower. So it will now follow whatever the reference voltage is and make the output voltage the same, because remember, an op amp will try to make both inputs the same. So essentially this resistor is now 0 ohms and this resistor is 50k thereabouts, and in actual honesty this resistor could now be simply out of circuit, disconnected, and it will still give us, well, keeps going up and down in voltage. That could be because of the pot. The output of 4 odd volts. You also notice that I've got this I limit input pin. That's for current limiting, which basically steals the base current from this transistor, so it limits the voltage coming out. The error amplifier will correct that, and it'll also prevent the thing from dumping shitloads of current into the load during a short circuit, for instance. So let's see what happens when we remove basically that gain set resistor, which is 50k. The voltage is still around what the reference voltage is. It made no difference. So that op amp now is operating as a voltage follower. If I increase the pot now, nothing appears much to happen. That's now because we've got no resistive gain set resistor. So if I reconnect that to ground, now the voltage is starting to increase, as it should. So we could basically set our reference voltage to whatever we want. So I'm going to get jiggy with it, and I'm going to drop this off just to be funny, 0.6 of a volt. And the multimeter is saying more like 1 volt. So I'll just change my multimeter probe to our reference voltage, 0.56. So there's a little bit of an error there, but it's not that significant to worry about. And I've just lost my reference voltage. Right, that's much better. It prefers to be running at 1 volt reference voltage as a minimum, and plus my wires came out. So yeah, between 1 and full supply voltage. So you could make a variable power supply out of this. However, if you wanted to achieve 0, how would we do that? Well, what we basically need to do is we'd need to supply the op-amp with a bipolar supply, so we'd have to give it a separate negative as compared to common. So as I've got 2 power supplies, I can easily do that. So the supply voltage should be probably a little bit higher than the reference voltage, and then we should be able to achieve 0. Whether or not we have to move this pot's ground point, which is in this case this red wire, from the common to the actual new negative, I don't know. But what I'm going to do is I'm going to set that experiment up and we'll have a look. Okay, the other power supply is powering the negative side of the op-amp at around about 5 volts. The Zener diode reference is back in circuit and the pot has not been moved. So we've currently got 9.27 volts on the output, so if I rotate down to minimum, still 5.2 reference voltage. Okay, so let me just switch the pot position to there. No. It still only works down to the reference voltage, which would actually make sense because even though the op-amp and the pot are seeing a negative rail or bipolar supply, the reference voltage is not. That was connected to the common ground. If I now connect the anode of the Zener diode to our new negative rail point, we're about halfway up on the control's rotation. .2 of a volt. Now, if we step our negative supply voltage up just a little bit more, to about 5.9, which is higher than the Zener voltage, we can get a -5 there. And if we used a little trim pot in series with the well, in this case the red wire, which is going to the new common, or negative I should say, I keep calling it common, we would be able to zero that out. So we can go from basically 0, 1 volt, 2 volt, 3 volt, 4 volt, 6 volt, 7 volt, 9, 10, 11, 12, 13.7. And then we run out of control. So as we can see, we've got a variable output down to 0 volts. So that is kind of cool. But the question is, if I put this at, say, I'm going to go 5 volt roughly. Okay, do we still get proper regulation on the output? That is when I connect up my 27 ohm load, sorry. Yeah, it's not too bad. With the load connected, we're still around about 5.1. With disconnected, we're still 5.1. So I'll bring that back to a 12 ohm load by joining the two resistors together again. Yep, it's still regulating quite fine. So, through this course of experimentation, we've actually come up with a variable power supply that can go down to 0. However, that was not the point of this video. The point of this video was to just experiment with the series pass regulator using a error amplifier. And so far what we know is we can get a 0 volt output by providing a voltage for the negative rail separate to the main power supply. which you can generate off of a 555 timer, etc. But it has to be higher than the reference voltage. So in the case of that, if you want a 5 volt negative rail, you'd probably go like a 3.3 Zener diode there. We've got to be careful with that too, that we do not exceed the maximum ratings of this IC's supply voltage rails. Remember, it's plus minus 18 volts or 36 volts DC across it. So you've got the added 5 volts here, negative 5 volts, so that has to account to your, be added to the positive side voltage that's going into the rest of the circuit here. So if it was 15.5 volt plus 5 volt, that means we now got probably 21 volt now DC across the supply pins of this IC. So you wouldn't want to put like a 30 volt DC supply, 35 volt DC supply or whatever on the input, because that'll be more like closer to 41 volt across that IC. So you'd have to get an op amp that has a higher supply rail. So what's the next thing to do? Well, the next thing to do would be to implement some form of current limiting. There are several ways of doing that. You can have a transistor here with the base connected to the emitter junction of the output stage, the emitter of that transistor connected to the output after the I-sense resistor, and the collector going back to the base of this transistor. You can use a transistor as a current foldback, so as the current increases it folds it back into the base and then drops the base voltage down, therefore limiting the current by dropping the voltage. Or you could use an op amp, or you can just go with the simplest form, which is just 2 diodes connected in series with the cathodes going to the output and the anode going to the base. What happens in this is once a 0.6 of a volt drop is developed across this I-sense resistor, this diode will start to conduct. The more voltage drop across this resistor, i.e. the more current that's being drawn, the more that this diode is going to conduct. Eventually this diode will turn on and then it will steal the base drive current accordingly to the output stage. That just means error amplifier, and that's the voltage reference just for, you know, simplicity. So I'll hook up 2 diodes now as in that configuration, and we'll see what happens when we put a load on it. So that's what these 2 diodes are for. I do actually have a string of 3. I've found that with the 2 diodes it limits the current to around 500 mA. If there's 3, it's about 1.8 amps. So for now I'll just use my 27 ohm. And well, it didn't drop that much. We've got close to 300 mA on the supply, 5.2 on the meter, so it's probably not much of a significant load to it, so not at that voltage anyway. So I'll connect both these resistors together in parallel with the output. Voltage is still around 5.1, current is roughly 500 mA. So I go to my 1 ohm resistor, which is basically like a short circuit anyway. Boom. The voltage dropped right off. So we've got 0.7 of a volt there and about 600 mA. So if I was to directly short the output now, it's actually more closer to 0.3 of a volt on the output and still 600 mA. So there's only 600 mA flowing through the output stage, so that should not be getting anywhere close to hot. So I'll just disconnect the short circuit now. And as we can see, the voltage has come back up and stabilised, well, almost stabilised at 5.2 volt. So we've just implemented short circuit protection, because if we didn't actually have that in circuit, I'll just disconnect it temporarily and I short the output, 6.5 amps, and the voltage only drops down to 4.6. So that's kind of nasty for that poor output transistor. So I'll just connect the string of 3 diodes in circuit now. So we have now a total drop across here of 1.8 volts before it actually will start stealing base current. You can look at the power supply. I'll short the output, 1.9 amps, 1.2 volts. As I said, you could use a transistor. I'll put that back to what it was. As I said, you could use a transistor to do the same thing. You can use a transistor in a foldback arrangement, which uses another resistive divider. There's plenty of circuits online that describe this technique. However, I could not get them to work satisfactorily, mainly probably because I'm using the wrong type of transistor with the incorrect gain requirements for it to work correctly. or my series resistor is, you know, not the right value, stuff like that. However, as I did say, we could use an op amp, but that's beyond the scope of this video. I may come back in the future and revisit that using the op amp to current limit the circuit. So you could get up to, you know, like 1 amp or something of current draw. So I would say that the maximum current draw you probably want to do on this circuit with the current components is about 3 amps, and the voltage should not drop off that much. So I guess it would be a good idea before I end this video to look at a final schematic so we can see exactly how the thing is wired. We've got our LM833 IC here. Pin 3 connects to a 1K2, in this case I said 3.3 volt. That's a good average voltage that you can give it as a reference. As I said, you can use whatever reference voltage you want as long as it's like 1 volt. But you can't get any Zeners, not locally anyway, lower than 3.3. That is connected from the positive incoming unregulated supply and our new negative 5 volt reference voltage down here. So you'd have plus 20 volt here, the negative of that side of the supply or common, and a separate negative 5 volt supply. As I said, you could generate that using a 555 timer, which I've done before. We're going through this variable resistor to pin 2, which is sampling output voltage into the error amplifier. This also makes it a variable supply from 0 to, well, 18 volt roughly at 500 mA current limited. We have a little trim pot down here, 1K should be enough, where we can actually adjust where that voltage is so we can zero this out, so it's not like giving a negative voltage or anything stupid like that. The output stage consists of a TRP35C and a BD139 configured as a Darlington transistor. That's our current sense resistor, which comes across these two diodes, and as I said previously, once 0.6 of a volt of voltage drop is developed across this resistor, then this diode will start to conduct, and the more it conducts, this one will conduct, and the more that these two conduct, will start stealing the base drive current to the output stage, limiting the voltage, which will in turn limit the current down. There are better ways of doing this than that, as I've said, but that's beyond the scope of this video. So you've basically got a 0 to 18 volt power supply with these current components. Yes, the circuit can be improved. We could add a lot more components to stabilize this op amp. I haven't shown the 100 nanofarad capacitor across the supply rails, but it is there in the actual circuit, but that's fine. That's kind of irrelevant for what I'm trying to demonstrate here. So yeah, I'm going to end this video here, and if you enjoyed it, please remember to go down below, comment, rate and subscribe if you haven't done so already. And this is the Astro 30 as always saying, see ya, have a great day, happy electronics.